All right, so in this video, I'm going to introduce the Frequentist Foundations chapter from the textbook. This lecture is actually very similar to the lecture that I have for the Bayesian statistics book. So if you have watched that lecture already, then you don't really need to go through this lecture. But if you're just taking my Frequentist statistics class, then you will need to go through this lecture. So you should also make sure to read um, chapter 1 of the textbook that I provided. And so now I'm going to walk you through the basic ideas that we need to be familiar with for understanding the frequentist foundations relating to distributions, discrete and continuous distributions, and bivariate and multivariate distributions. I'm going to start sharing my screen now. Okay, so these are the slides which I'm going to put up so that you can access them later on. So basically, as I discussed in the class as well, we are always going to be confronted by data in one form or another. And these data that we will encounter in experiments would um, would need to be thought of as being produced by a mathematical or statistical process, right? So there's an underlying mathematical object that we're going to assume is producing the data. And that mathematical object is called a random variable. And so the way a random variable is defined, so you always use some variable name like X or Y or Z or whatever variable name to represent this underlying object that's producing is assumed to produce the data that we are encountering in an experiment. And so mathematically this random variable is a function that associates with every possible outcome that we might observe in an experiment. So the outcome could be the results of a coin toss, like a 0 or 1, 0 for tails, 1 for heads, or it could be reading times in milliseconds, or it could be electrical responses on the scalp in microvolts. So that's what I'm calling an outcome. So these could be any numerical value in the case of reading times or um, ERP responses, or it could be 0, 1 responses. So that's what I mean by outcomes. So associated with each outcome is going to be one number. So that's what this function does. It takes every possible outcome and associates with it a real number, right? So that's the real number system that is being mapped onto in this function. Okay. So, all the possible values that a particular random variable could produce, these are going to be represented as a set, could be a finite or infinite set, right? And that set will be called S of X, where X is the random variable. So, um, so every possible, numerical value that we are associating with each outcome is going to belong to this set, which is called the support of X. Okay. So just to give you some examples, okay, so let's start with a very simple example, which is what we call a discrete random variable. Discrete means discrete is the opposite of continuous. Okay, so I'm going to make that contrast very soon, so you'll see exactly what is meant by discrete. But to take a concrete example of a discrete random variable, consider the situation where you start tossing a coin successively. So you toss a coin once, okay, and you keep tossing the coin again and again until you get a heads, right? So what could happen is you take a coin, you toss it, you end up getting a tails. So in that case, you toss it again. And the second time you might get a heads, right? So these are possible outcomes. One possible outcome could be that you toss the coin just once and you get a heads already. So you stop at that point. So we keep tossing until we get a heads and then we stop. Right? So in that situation, what does the random variable look like that is assumed to produce the data that we will get, that we could get, you know. So, so the random variable is now going to be mapping every possible outcome to a numerical value. What are the possible outcomes? These are listed here. So you could get a heads right away, you know, when you start tossing, or you might have to toss twice before you get a heads, or three times, etc. So this, I mean, it in theory, you could be in a situation where you have to toss many times until you get a head. So the actual outcome space, you know, would be infinite in principle. So what the mapping is, you know, this mapping here that I'm talking about in the random variable, if you get a heads, then the random variable assigns the value 1 to that particular outcome. Okay. If you have to toss the coin twice to get a heads, then the random variable assigns the value 2. If you have to toss the coin 3 times to get an X, then the random variable assigns the value 3, and so on, right? So the support of X is going to contain the discrete numerical values 1, 2, 3, etc., all the way up to infinity, right? So that's the support of X here, this set here, right? So the reason it's called a discrete random variable is that you can't have 1.5 coin tosses. Between 1 and 2, there's nothing, right? So that's why it's a discrete random variable. So another example is a very simple one again, tossing a coin just once, okay? And there, the possible outcomes are heads or tails. Let's not consider the possibility that the coin lands vertically, okay? Even though theoretically it's possible. So you got heads or tails are the possible outcomes. That's your small omega. And if you get a tails, we are conventionally going to represent that as a 0. So that's the numerical mapping, right, to the real number system. And if you get a heads, then that's 1. Okay? So that's another example. So the support of X now is the set containing the numbers 0 and 1, right? So that's an example of another example of a discrete random variable. So what's interesting about this whole formalism, you know, of random variable theory is that associated with every random variable will be, in the discrete case, associated with a discrete random variable will be a probability mass function. And later on, I will introduce a continuous random variable, and there, associated with the continuous random variable will be a probability density function. So these two important terms are being introduced now: probability mass function associated with discrete random variables, and probability density function associated, which is associated with a continuous random variable. Okay, so let's consider discrete random variables for the moment and talk about probability mass functions, so PMFs, right? So the probability mass function in a discrete random variable will be a function which I'm representing as P of X, which takes every element in the support of X and maps it to a number between 0 and 1, right? Why 0 and 1? Why is the range delimited to 0 and 1? Because with every possible element in the support of X, we are mapping every possible element in the support of X to a probability. So we are assigning a probability to every possible thing that can happen in the experiment, right? So basically what we are saying here is that with the probability mass function, we can look at every element in the support of X and figure out the probability, that's the probability here, of obtaining that particular element in the support of X. So mathematically, we would write it like an equation too, right? What I just said in English would be written down compactly in this equation here, yeah? That the probability of X, where X is an element in the support of X, is going to be whatever the probability mass function tells us it is, okay? So let's take a concrete example now, okay? So suppose we're talking about a fair coin. By fair, I mean that it's not biased to produce heads only or tails, right? Or biased to overwhelmingly produce a heads or a tails, right? In the case of a fair coin tossed once, let's say, right? The support, as I said, can be a 0 or 1, And the probability of each possible event, right? So here, what I'm talking about, um, uh, events here is this 0 or 1 that we get, anything that can happen in a particular experiment, right? So the probability will be determined by the probability mass function. So let's decide for now, because it's a fair coin, right? Heads and tails are equally likely. So let's say the probability of each of those two things that can happen is 0.5. Okay. So now we're going to find out how this probability mass function is actually defined. Okay, so but what it will do, what this probability mass function does for us in this single coin toss example, is that for every possible value like 0 or 1, right, it assigns a probability, namely 0.5. Okay, that's what this probability mass function does for us. So this is a definition here of the probability mass function, right? Now, one can also use the probability mass function to define another function called a cumulative distribution function, or CDF, which is conventionally written with a capital F. Okay. And what this CDF does for us is that it tells us the probability of observing a value like X or something smaller than that. Right. So mathematically, F tells us the probability, this capital F tells us the probability of observing a value like X in the random variable capital X or something less than that. That's what this sign means, right? So, for example, if I write capital F X equal to 1, what I'm actually asking is, what is the probability of observing 1 or something less than that? So what's the probability of observing 1 or something less than that? Well, it has to be 1, because what that amounts to saying is that the probability of observing 1 or observing 0, that means heads or tails in a single coin toss, will have to be the sum of the probabilities of observing 0 and of observing 1. And because each of these probabilities is 0.5, I defined that here in my probability mass function. The cumulative probability of observing 1 or something less than that has to be 1, right? So that's the purpose of this cumulative distribution function. This is the information that it gives you. Yeah? So for in a similar way, you can ask, what's the probability of observing something like 0 or something less than that? Well, there's nothing less than 0 in this particular experiment, because the only elements that we can get in the support of X is 0 or 1, right? Therefore, the cumulative probability of observing 0 or something less than that is going to be 0.5, because it's just the probability of observing 0, right? So that's the purpose of the cumulative distribution function, to give you this cumulative probability. And you'll see very soon why that's needed. Okay? All right, so let's consider now a somewhat more complicated scenario where we toss a coin not once, but 10 times. Okay? So the number of trials that I will have is 10. Okay? And let's assume that the probability of getting a heads is 0.5, because the coin is fair. So we're going to use this library called extra distr, which you'll have to install if you don't have it installed already. And what I'm doing here is I'm taking a function inside the extra dist library, and I'm running that function. So this is called RBARN. R stands for random. BARN stands for the Bernoulli random variable. Okay, so the Bernoulli random variable assumes that each coin toss is being modeled by a random variable where the probability of success is something, some number between 0 and 1. I'm assuming 0.5 just for illustration. Okay. I could have chosen some other number between 0 and 1 here. Okay. And so here I'm running what we would call a Bernoulli process. Basically, I'm tossing the coin 10 times, and those 10 coin tosses, each one of them is a Bernoulli process. That means each one of them is producing a 0 or 1, just like what I just explained, Here it's producing, each trial is producing a 0 or 1, but I'm doing it 10 times, okay? So each one of these zeros or ones that is being produced in those 10, trials that I've run. So what you're seeing here in the output of RBAN is that you are seeing the results of a actual experiment that I've run on the computer. If I were to run this over and over again, let me do that. Okay. Let's pull up RStudio. Okay. And let's just run this function over and over again, right? So what you will find, oh gosh, what is this? Extra distro. Double colon means look up the function in that library. So the function I'm looking at is rban and run 10 instances of the Bernoulli process where the probability of success is 0.5. When I do that over and over again, you'll see that the number of the sequence of successes and failures, so heads and tails that I'm getting, are randomly varying each time. Okay. And in fact, if I had to change, if I were to change the probability of success to be, let's say, 1, okay, then what would happen is that every time I run this simulated experiment with 10 trials, I'm going to get a heads every single time. Now there will be no variability, right? Or if I set the probability to 0, I would get tails every time, right? So the probability is actually controlling the probability of getting a success here. And it's going to vary from one trial to the next. You can see that it keeps changing, right? All right, so this is the result of a random process. Like I toss a coin 10 times. This is a simulated experiment. Of course, I could have, let me see if I have a coin in my pocket. Okay. So I could have taken this coin and actually tossed it 10 times. I'm not doing that because I'm lazy, right? So I'm going to actually do this on the computer. So I'm literally simulating an experiment on the computer here. Okay? And so the probability mass function that will give me the probability of success in every single one of those 10 cases, right, is defined like this. Theta here is the probability of getting a heads, and X is a 1 or 0. Those are the possible things you can have in the support of X in a single trial, right? So this equation is giving me the probability mass function of, x equal to 0 or x equal to 1. But theta, I will have to specify. I'll have to give the value theta, some value between 0 and 1 to theta, like I just did. I gave 0.5 here. And so once I decide on a probability of success, I can compute the probability of getting 1 or 0 as one of the things that can happen in this experiment. So in order to figure out, with a given a probability mass function, in order to figure out what the probability would be of each of the possible things that can happen, there is a function um, built into the extra dist package. It's called the dban function. D here stands for density, but actually what this is it's a probability mass function. Okay. So I will explain why it's called D in a moment, right? But what it's telling me, what this dban function is doing for me, is it's telling me the probability of observing 0 or the probability of observing 1. So I change this number to decide which probability I'm asking about, and it's going to give me back a probability for each of the possible elements in the support of X, right? And so here, of course, this is very trivial what I've done because I already specified the probability of success. Whatever number I put in here is the number I'm going to get out here, right? But very soon you will see the importance of this D family of functions when we get to other distributions, right? So notice also that the probability of getting 0 or 1, right, will have to be the sum of these two probabilities, because the only possible things that can happen is that you could get a 0 or you could get a 1, right? So if I ask you what's the cumulative probability of observing 1 or something less than that, that would have to be the sum of these two. And that's what I computed earlier with the cumulative distribution function. So you can see the connection between the probability mass function and the cumulative distribution function. These two guys are intimately related to each other. We use the probability mass function to define the cumulative distribution function. And you saw that here. Here, I'm using the probability mass function to calculate the probability of observing something like 1 or something less than that, right? So I'm actually using the probability mass function to define the cumulative distribution function. So the cumulative distribution function and the probability mass function, they're just two sides of the same coin, right? All right, so where was I? Here, right? So this is an example of a single trial and how I can compute the probability of getting a 0 or a 1 using a built-in function in R. This is the dban function. And I can generate random data from a Bernoulli process using the R-ban function, okay? And right. So as I mentioned, the cumulative distribution function that I just defined as the sum of all the probabilities of every possible, element x or something less than that, right, is defined in R through the so-called P family of functions, P for probability, right? So if I type P ban, and then I write 1 and define the probability of success here, what this p-band function is doing for me is that it's computing the cumulative probability of observing 1 or something less than that. That's what this function does. So this is a convenience function for us, which actually implements in the software the cumulative distribution function, right? So what I've shown you is three important functions: the R-band function for generating random data, the D-band function for computing the probability of every possible element in the support of X, and the p-band function for computing the cumulative probability of a value X or something less than that. Okay? So these are three important functions that we're going to use. So I could use the p-band function for the value 0. Now I'm asking what's the probability of observing 0 or something less than that? Well, there's nothing less than 0, right? Therefore, the probability of observing 0 or something less than that is the probability of observing 0, which is 0.5 in this particular example. Okay? All right. So the main points that I wanted to get across here is an example of a discrete random variable. The simplest one we can think of is the Bernoulli, right? Random variable. I've shown you how to generate random data with a Bernoulli with the R-band function, right? So if you see this, I could actually I could literally produce oh, sorry, literally produce a Bernoulli process like this, right? Here I'm tossing a single coin once, exactly once, right? But if I were to decide to toss the coin 10 times, then I have 10 Bernoulli processes in action. So the number of trials that you have is determined here, right? Okay, so that's how you generate random data with the R-band function. The D-band function is giving us the probability of different possible, things in the support of X. And the cumulative distribution function is giving us the cumulative probability of observing a value like X or something like that, right? So you should be reading chapter 1 of the textbook at this point. So please don't forget to do that. You shouldn't just watch these lectures and hope to understand everything, okay? You need to read the material provided. Okay, so now I want you to consider a situation where we toss the coin 10 times instead of once, okay? So the way we will do this is that, of course, each of those 10 coin tosses, each one of them is a Bernoulli process, okay? And I showed you the probability mass function of the Bernoulli process, but now we are talking about 10 coin tosses. And for 10 coin tosses, we can define another random variable that is actually closely related to the Bernoulli that is called the binomial distribution. So this random variable, the binomial random variable, has associated with it another probability mass function, which looks very similar to the probability mass function for the Bernoulli, except that the binomial probability mass function tells us the probability of observing um, a value like x, where x is an element in the support of x, for more than one trial, right? So if you have n trials, this probability mass function will give you the probability of observing any of those possible events that can happen, right? So the support of X now for 10 trials can lead to the following possible event. You could have 0 successes. Let's say you toss a coin 10 times, you could get tails each time. It's unlikely in a fair coin, but it can happen theoretically, right? You could have only one heads, or you could have um, two heads or three heads or four heads. So there are 11 possible events, in an experiment where we are tossing the coin n times, okay? So n will represent the number of times that the coin was tossed, okay? In R, this will be called size. I'll show you in a moment. And this part here in the probability mass function for the binomial is counting the number of ways you can get the event X. So for example, if X is 1, that means you got one success out of 10. There are actually 10 possible ways in which you can get it, right? So you could have success, so heads, followed by 9 tails, or you could have tail. The first coin toss would give you a tails, and the second one would give you heads, and the rest of the 8 would give you tails. Or you could have the first two trials giving you tails, the third one giving you heads, and the rest of them giving you tails. So there are 10 possible ways in which you can get um, one heads, right? So, or you can get, there are 45 possible ways in which you can get two heads given 10 coin tosses. So that's what n choose to, this n choose x is doing for us, what this function is doing for us. It's just a standard combinatorics function that you will find in any permutations and combinations chapter in mathematics. Maybe you've done this in school, right? How many ways can you get a heads when you toss a coin 10 times? That question is being answered by the choose function here. And so this choose function, n choose x, is part of the probability mass function. And so let's see where this takes us now, okay? And theta, of course, in this equation is just like in the Bernoulli, it's the probability of heads or probability of success here. Yeah? So let's visualize the binomial random variables probability mass function graphically. Okay, so graphically what we are looking at is this is the support of x. If you look at the x-axis, you can get 0 heads, 1 heads, 2 heads, etc., all the way up to 10 heads. And these bars that you're seeing, they're giving you the probability of each of these possible events, right? And the height of the bar is telling you the probability. So for example, the probability of getting 5 heads in 10 coin tosses, assuming that the probability of getting heads is 0.5, is going to be this this number here, right? Whatever this number is on the y-axis, okay? I can't get to exactly that value, but it's a little bit under 0.25. I'm going to show you how I get this probability, okay? I'm just going to show you how to do that. If, however, so this was the situation where theta was assumed to be 0.5. Theta is the probability of success, right, of getting heads. If I change the probability of getting a heads to 0.1, for example, then the shape of the probability mass function changes, right? This is the shape of the probability mass function. It's symmetric, right? The maximum point is at 0.5, but if I change it to 0.1, then the maximum point is over 1, and the binomial distribution function, this probability mass function, changes its shape. So it skews, so that skews to the right. So it gets crushed towards the left because I mean I've lowered the probability of heads here. If I change the probability of heads to be 0.9, then the probability mass function shifts to the right, right? And it skews to the left now. Okay? All right, so there are four, important functions that we are going to learn associated with the binomial. I already showed you three from the Bernoulli. I'm going to present those three again for the binomial plus one more. Okay, so let's see. First of all, we are going to use, just like we use the R-Bairn function to generate random data from a Bernoulli random process, right? We are going to generate random data from a binomial process. So now I'm going to show you how we can produce random data. So here's the R binom function. This is built into R, so you don't have to load any library for this. Here I'm assuming that the probability of success is 0.5. Why am I assuming that? Just because I feel like it. Okay. Talking about a fair coin here, I could have chosen a different probability just to generate a different set of type of outcome. Okay. So what I'm doing here is I'm producing um, 10 uh, 10 trials here, and size is equal to 1. That means that each time I'm tossing the coin once, and I'm doing that 10 times. And so I'm getting 0 and 1 sequences, which is just like the R band that I produced earlier, if you remember. So this function that I'm writing here, that you're looking at, is exactly the same thing as typing R band as I did earlier. So you see this? So I had this statement that I had written, right? This statement that I had written was also producing a sequence of zeros and ones 10 times. And so this R Bernoulli function is assuming that size is equal to 1. That means each time I'm just tossing the coin once. And so I can do the same thing as in the Bernoulli process by using the R binomial function. So you can see the connection between the Bernoulli and the binomial. They're actually the same thing. It's just that the only difference here in the binomial is that we can have size larger than 1. Okay, so for example, what does the size do in the R binomial function? What size does is that I can now simulate the situation where I'm tossing the coin 10 times, okay? And I'm going to do the experiment 10 times now. Each time I will toss the coin 10 times, and I will do the experiment 10 times. So what that will give me, each time that I run the experiment with sample size 10, I'm going to get a number like 0 to 10, some number between 0 and 10, 0 or 1 or 2 or 3 or 4, and so on, all the way up to 10. So for example, in the first experiment, I got 5 heads. In the second experiment, I got 8 heads. Third time, I got 2 heads. And then I got 6 heads. If I keep running this function over and over again, I will get different sequences of heads. Again, this is a random process, right? We are simulating a random situation, right? You're not going to get the same results each time, right? And so what we are doing here is we are doing an experiment on the computer itself. What I could be doing right now, is that I could take my coin here and toss it 10 times, record the number of heads I get. That would be this first one here. So let's say I get 6 heads, I would write 6. Then I would toss the coin again 10 times. Then I could get maybe 5 heads. Then I would write 5 here, and so on. It's that situation that I'm simulating on the computer right now with the R binomial function. So I hope that's clear. Okay. All right. So because as I said, there's 11 possible things that can happen. You could get 0 successes, 1, 2, 3, all the way up to 10, right? So what I can now do is I can now calculate the probability of each of these possible things that can happen. So there's 11 possible things that can happen. X can range from 0 to 10. So I'm computing the probability of each one of these possible things that can happen, and that's in this row here. And the way I'm doing it is by literally computing this function, this probability mass function, this one here. I'm going to replace n with 10. X will be whatever number I want to know the probability for. X equal to 0, X equal to 1, right? So X will have that value. Theta will be whatever I believe the probability of success is going to be. And once I plug in all these numbers, I'm going to get back the probability that you saw in these bar plots also, right? But which I'm now writing down in a table. So these are all the probabilities. If you remember, I'd shown you graphically the probability of getting 5 heads in 10 coin tosses when the probability of success is 0.5. I showed that here. That's a number very close to 0.25, and that number is exactly 0.246 here. Okay, so that's what I'm doing here is I'm computing the probability of every possible outcome, and I'm doing it using the D binomial function, right? So what I'm doing here is I'm I'm computing for every possible number between 0 and 10, right? So 0, 1, 2, 3, 4. That's that vector there. I'm running an experiment of size 10, okay? And I'm calculating the probability of getting 0, of 1, 2, 3, 4, all the way up to 10, assuming the probability of success is 0.5, and I'm rounding the probability to 3 digits. So that's why you're getting the probability up to 3 significant digits. So what we say is, when we have 3 digits after the decimal point, we say that we are computing the value up to 3 significant digits. Okay. Now, that was the D binom function, which gives me the probability of every possible thing that can happen. We can also compute the cumulative probability using the cumulative distribution function. So I can ask a question like, what's the probability of observing 0 or less than 0 successes, 1 or less than 1 successes, 2 or less than 2 successes? That is computed using the P family of functions, as I showed with the Bernoulli earlier, right? And now you see the relevance of the P family, because now I can ask for the cumulative probability of observing any of the possible things that could happen. That's in the support of X, right? For an experiment with size n and probability of success 0.5. And so what we are getting is 11 numbers here, which I've plotted graphically here, which is showing me the cumulative distribution function, the CDF of the binomial random variable. So what this figure tells me is I can just eyeball this figure and look at it, and it tells me the probability of observing 7 or something, or a number less than that. That would be this number here. The probability of observing 10 or less than 10, right, will have to be 1, because 10 or less than 10 successes is all the possible things that can happen anyway, right? So that's why this probability, cumulative probability, would be 10. But importantly, what I can do is I'm drawing this plot by using the p binom function. So what I'm doing is I'm just computing these probabilities, and these probabilities are showing up as the heights of um, you know, um, these bars for every possible value between 0 and 10. Okay, so now you see the payoff of knowing a little bit of R. You can actually graphically summarize any probability mass function, right? Like we did earlier. You can graphically summarize a probability mass function for a discrete random variable, and you can plot the cumulative distribution function with these simple plots here, right? The code for this plot I will show you later on. I'll give you the R code so you can run the code yourself, and you can reproduce these plots yourself after you watch the lecture, yeah, when you're reviewing the material. So now I'm going to introduce a new function. I've introduced the R binom, the D binom, and the P binom functions. I'm going to introduce another function called the Q binom function. Okay, so what the Q binom function does is that it answers the following question. It answers the question, what is the element X, which I'm calling Q here for a moment. I'll explain why in a second. What is the element X such that the probability of observing that element or something less than that is the value P. P is the probability here, right? Now, these elements X, so these elements X, these are also called the quantiles of this distribution. So that's why this is called a uh, Q here instead of X, because I'm asking which quantile is it such that the probability of observing that quantile or something less than that is the probability P, right? That's the question that the function, where is it? Sorry, Q binom, this function is going to answer. So what I'm going to do here is that first of all, I use P binom to calculate the probability of observing 0 or less than that, 1 or less than that, all the way up to 10 or less than that in this particular experiment that I'm simulating. So that was the plot I just showed you. Yep. I've computed these probabilities, these probabilities, and I've saved it as a vector probs. And what I'm doing is I'm taking that vector of probabilities, plugging it into the Q binom function, and what I get is a plot that looks like this. So what this Q binom function is doing is that it's taking as input a probability, and it's telling me which quantile that probability corresponds to. So it's answering this question here. So basically, this Q binom function is the inverse of the P binom function, because the P binom function takes as input a quantile and returns the probability of observing that quantile value or something less than that, right? The Q binomial function does the opposite. It takes a probability and it returns a quantile that corresponds to that probability in the cumulative distribution function, right? So the inverse of the CDF is the Q binomial function. Okay? So here's the big insight, right? For a particular discrete random variable, in this case, the example I'm showing you is the binomial random variable. There will be four functions that tell you everything about that particular random variable. These are called the DPQR family of functions. R is producing random data for you, and we will be simulating data in this course, to get an understanding of how random processes work, how experiments play out. So that's the R binomial function. The D binomial functions tells you the probability of every possible, thing that can happen. The P binomial function tells you the cumulative probability of a particular event that can happen or something less than that, like 6 successes or less than that. That's the P binomial function. And the Q binomial function is the inverse of the CDF, inverse of the P binomial function. Okay. So I've demonstrated how this works now. All right, so summary. Okay, just to summarize what I've said all this up to this point, I'm talking about random variables. A random variable is a function, right? That, well, I had used omega earlier and I've switched to S here. I'm going to fix that in a moment, okay? That associates with every big omega element, every possible outcome, it associates with it a real number, right? And I give you examples of that. That set of real numbers that the random variable maps each outcome onto, right, is called the support of X. I gave you an example of that as well. And we are talking, the example that I've discussed so far is the discrete random variable, right, which has associated with it a probability mass function, right? And so the probability mass function looks at every element in the support of X and assigns a probability to it. That probability assignment in R is computed using the D family of functions, right? So the D binomial function, right? And you can compute, of course, cumulative distribution functions by summing up the the probability mass function, or you can use the P family of functions to compute a cumulative probability. And so these functions that I showed you for the Bernoulli, R band, D band, P band, and of course there is a Q band function also, right? Is also showing up, that DPQR family of functions is also showing up in the binomial discrete random variable. And I showed you how each of these four functions plays out and how you can actually use this function. So the big upshot here, the big upshot of this discussion so far is that we now know how we can describe a random generative process of an experiment where you're getting correct and incorrect responses. So the practical application of this would be, you could be doing an experiment where you're asking subjects yes, no questions, and they're giving you correct or incorrect answers. So that's the outcome that you're getting, out of each experiment. And so in a particular experiment, let's say you ask a subject 10 questions, you could get 5 correct answers or 8 correct answers from each subject, right? That's the process that we are simulating here using these the R binomial function to generate random data, right? And the reason we are generating random data is to try to understand the properties of a random process like the one that I'm describing right now, right? And the DPQR family of functions is important to understand because these functions tell you what you can do with a distribution, a probability mass function that you're assuming for a particular experiment that you're running. So if you're asking yes, no questions in an experiment, you're assuming a binomial process, right? If you have 10 trials in every experiment, then you're assuming a binomial process with size equal to 10, okay? So now you can ask all the relevant questions that you could theoretically ask in this scenario, right? And the DPQR family of functions is designed for that purpose. Okay, so let me come back to my slides now. Right. So let's move on to the second class of random variables that I want to introduce, right? So I introduced discrete random variables. Now I'm going to talk about continuous random variables, right? So continuous random variables are variables where the support of x, of the random variable x, is no longer discrete outcomes. Like with coin tosses or asking questions, you can have 0 successes, 1 successes, 2 successes, 3, all the way up to 10 for 10 trials. You can't have 1.5 successes, right? But in a continuous random variable, you can have any number in on the real number line. So between the values 0 and 1, for example, right, in the support of x, you could have an infinity of possible values. Between any two numbers, you could have an infinity of possible values, right? That's the definition of that's what a continuous random variable will be. So for example, we could be talking about reading times. Reading times in an experiment will range from 0 in principle all the way up to infinity, right? Of course, you're not going to observe infinite reading time, but in principle, it could be a positive value going from 0 upwards, right? But it could be any number. It could be 400 milliseconds. It could be 400.0000001 milliseconds, right? Or 400.002 milliseconds or something, right? The resolution of, the granularity of the precision that you get is limited only by the machine that's recording the reading times, right? So uh, obviously you're not going to get infinite decimal points after the decimal point. You won't get infinite digits after the decimal point, but in principle you could. If your computer had enough granularity, you could do that, right? So continuous random variables have associated with them a probability density function. So remember, with discrete random variables, what you have associated with a discrete random variable is a probability mass function. With a continuous random variable, you have associated with it a probability density function, right? So in brief, what we say is that it's a PDF, right? PDF stands for not a PDF document, but a probability density function, okay? And so we're going to write the PDF for a random variable like this. So whenever we want to talk about a continuous random variable, which has associated with it some PDF, f, I'm just calling the function f, we're going to write it like this. So the way I'll say this, equation 5, is that x has associated with it a probability density function f, and this thing here is the symbol called tilde, tilde. In LaTeX, you can produce the tilde like this. So let me just produce some LaTeX code, right? So I could type x, oh, sorry, where is it? X, oh, sorry, x tilde, right? Tilde f, oh, where is it? Sorry, c dot, right? So this should work, right? Oh, what have I done? I'm sorry about that. Oh, sorry, it's not tilde. It's called tilde, but it's written sim, right? Right. So this is what I'm producing here, right? That's what I'm writing here. This thing is called tilde, but in LaTeX it's written \sim, right? For simulating, right? So what we are doing is we are assuming that the data that we are observing is coming from a random variable called capital X. And those data are coming from this distribution function, from this probability density function, right? So let's look at an example, okay? So here's a probability density function that could be assumed to be producing some data X, okay? Some data that's in the support of X, right? So just for simplicity, I'm assuming that X can vary from minus infinity to plus infinity. So the support of X in this random variable is an infinite set. S of X is an infinite set that ranges from minus infinity to plus infinity, okay? So what I'm showing you here is a function in the equation 6. It's a function where there are two parameters, mu and sigma, that I could decide on. Remember earlier with the Bernoulli distribution, I had a parameter theta. Where is it? Where is it? Where is it? Where is it? Here, right? I had this parameter theta that determined the shape of the distribution. The shape of the distribution is determined by the parameter theta. That's what I'm doing here, okay? So similarly, the shape of the probability density function in this particular continuous distribution that I'm showing you is determined by two parameters, mu and sigma. And of course, I'll discuss this in more detail later. And this complicated looking formula here is actually, if I plug in some value for mu and sigma in this equation, and I take an element from the support of x can be any number between minus infinity and plus infinity, I will get a number back which tells me the shape of this distribution for different values of x, right? So in this function, I'm going to put in different values of x, where x ranges from minus infinity to plus infinity, and I'm going to get a number back that I can use to draw a curve that shows me the shape of the probability density function. So let's take a look at how this works, okay? This this function that I just showed you, this is the function associated with a familiar normal distribution function. So you must have in your life at some point or another seen this, what they call a bell curve. Okay, so let me just see if I can pull up my iPad, right? Right, so here, so there's this characteristic function that you must have seen at some point or another. On the x-axis is the support of x, okay? And this is called the normal distribution. It's also called the Gaussian distribution after the named after the person Gauss, who was famous mathematician slash statistician working in Göttingen, not far from Berlin. So he basically came up with this distribution. So it's often called the Gaussian distribution, but it's also called the normal distribution. And this distribution, this curve that you're seeing, right? These for every value of x, there is some value that gives me the shape of this curve. These dots that I'm drawing here, these values are being computed by the function that I just mentioned. And the function has two parameters, mu and sigma. And what this function is doing is I'll take an x value and I can figure out what the result of that function is for that x value. And if I connect all the x values result, from the function, I get this curve, right? So for example, let's do this, okay? So if I were to put in mu equal to, I'm going to do this, okay? So let's say mu is equal to 0 and sigma is equal to 1, okay? So I'm going to write this function out now. For x vertical bar, mu equal to 0, sigma equal to 1, I'm going to write 1 over 2 pi sigma squared was the equation, exponential, and I introduced the exponential uh, in the last class, right? Minus half times x minus mu over sigma squared. That's the equation, okay? So mu is equal to 0, sigma is equal to 1. Sorry, this is sigma, right? So I'm going to rewrite this 1 over square root of 2 pi. Sigma squared is 1, right? So I'm going to remove that. It's not there anymore. And so here I've got, let's do this with square brackets, okay? So minus half, and then x will be whatever the support of x is. Mu is 0, right? And sigma is 1. So what happens here? What does this become? X minus 0 is x, divided by 1 is still x, so this becomes x squared. So this becomes 1 over square root of 2 pi exponent minus half x squared, right? That's what I end up with. So now this function is, I'm going to plug in a value, okay? So let's say x equal to 1 in this function, given mu equal to 0, sigma equal to 1. what do I get? 1 over square root of 2 pi times negative half times, what is it? Sorry, that's wrong. Let me just fix this. Sorry, 1 second. Right, so I still need the exponential term here. So exponent negative half, and what was x? X is 1. So, so exponent of negative half, what is that? Let's look it up. Yeah. Exponent of negative, oh, where is it? Sorry. Why is this not working? Exponent of negative half, okay, negative 0.5. I get a number here, right? So the result of that calculation that I just did is, where is it gone? Here, right? I'm going to compute this right-hand side now, this right-hand side now. It's 1 divided by square root of 2 pi, 2 times pi. Pi is actually a reserved word in R, okay? Okay? 22 over 7 is pi, okay? So it's 1 over square root of 2 times pi, okay? That's my first term. The second term is times exponent of, what is it? Minus half, right? 0.5. 0.5, right? So that's 0.2419707 is, I'll just call it 0.242, okay? I'm just gonna call it 0.242. And so what I've just done is for f of x equal to 1, given that mu is equal to 0 and sigma is equal to 1, gives me the number, I already forgot what it was. 0.242, that's 0.242, right? So I just did this calculation by hand, but now I could just keep plugging in different values for x into this function, and I would get different numbers here, right? Which allow me to plot, let me go back here, allow me to plot for different values of x, right? Allow me to plot this curve. Okay, so let me do this for you, okay? It turns out that the d norm function, will take different values of x and different values of mu and sigma, right? If you define mu and sigma, you can draw this curve. So I'm going to do that for you right now, okay? So let's do this. So let's define a sequence of values. So now you see the advantage of knowing a little bit of R, okay? Sequence of values going from minus 10 to 10 by 0.01. So I've created a sequence of numbers, okay? So that's my sequence of x values. And what I'm going to do is I'm going to plot on the x-axis the x values. And on the y-axis, I'm going to take the d-norm function, which I told you is the actual probability density function for this normal. I'm going to give it all the x values, and I'm going to specify the mean and standard deviation, the mu and sigma that I mentioned earlier. I'm going to plot this as a line, okay? And so you take a look at what I get. See that? What I'm looking at now is the actual probability density function for different values of x, and this curve is being defined by that equation that I showed you just now. This equation here, okay? All right, for different values of mu and sigma, you can draw different curves here, right? Mu is called the location parameter. It's the mean of the distribution. And sigma is called the scale parameter, which is here representing the standard deviation. Standard deviation actually controls how wide this distribution is. So if I increase the standard deviation in my R code just now, okay, so where's my R? So instead of using standard deviation 1, suppose I change it to 100. Look at what happens. Or let's change it to 10, okay? Look at what happens to the curve. See, it becomes much more spread out, right? Within that same range, the curve becomes much wider. So the standard deviation controls the spread. The mu parameter controls the center point. If I were to change the center point, look what happens, okay? If I change the mean to, let's say instead of 0, I change the mean to 3, okay? Look at the center point of the distribution. It's shifted to 3 now. The 3 is now 3 is the center point of this distribution, the maximum point of this distribution. You can see that the curve has moved to the right. So the mu controls the center point and the sigma controls the width of the distribution. Those two parameters have that functionality here, okay? So this normal distribution is an example of a probability density function in the normal random variable. It's a very important distribution because it's often the basis for almost all the statistical modeling that we will do in at least this first part of this course. Okay. Okay. So remember what, so now there's a very important difference that comes up between the discrete random variable and the continuous random variable. Okay. Remember, in the discrete random variable, I can compute the probability of any one of the particular events. So in the support of X, if I have 0 to 10 possible values for successes, I can compute the probability of every one of them using the d-binom function, right? That's in the d-binom function, I could do this. In the d-binom function, I could do this too. Here's the probability of getting exactly 2 successes in 10 trials, okay? In a continuous distribution, probability, the probability of observing some event is defined as the area under the curve. So a consequence of that is that for any particular point value, x, the area under the curve is always going to be 0. Therefore, the probability of observing any particular value in a continuous random variable is going to be 0 by definition. Okay. So let me remind you how this works. Okay, so in the discrete case, if you remember, we had set up a discrete random variable with a probability mass function that we had specified, and for particular parameter value for theta, we had this particular probability mass function. So for every possible element in the support of X, I can actually compute a probability now. And notice that the total probability of, observing any one of these values has to sum to 1. That's a property of a probability mass function and also a probability density function. So when I'm talking about the normal distribution, the same property holds, namely that the area under the curve, which is representing the probability now, the area under the curve has to sum up to 1. This area under the curve has to sum up to 1. Because the area under the curve now represents the probability of observing anything that is in the support of X. And if I look at the totality of everything that could be observed, the cumulative probability of observing any one of those events has to be summing up to 1, has to be 1. Okay. So that's why the area under the curve has to sum to 1. Okay. In the continuous distribution. And so you can now imagine the complication here, right? So where was I? Sorry, lost my place here. Yeah, I was here, right? So what I'm trying to say here is that in a continuous distribution, the problem that we face, of, let's say we have a continuous distribution like this, defined to go all the way from minus infinity to plus infinity, right? Because this is a continuous distribution, the number of numerical values you would have between any two arbitrary numbers here. Let's say this is 0.1 and this is 0.2. The number of values that you have between these two numbers is infinite, right? So you have to now ask the question, how can I figure out the probability of every element under the support of X, right? You can't actually just do the discrete random variable thing and just say that, oh, this is the probability of, getting 0.1. This is the probability of getting 0.2. You can't do that because there's going to be an infinity of possible values here between any two arbitrary numbers. And you have the constraint that you want to make the probability sum up to 1. How are you going to do that if you have an infinity of possible values on the entire x-axis, right? So the probability of observing a particular number like 0.1, 0.2 will be defined as the area under the curve, and the area under the curve at any point value will have to be 0, because the area under the curve can be approximated as, a rectangle like this with a certain width and a certain height. But if the width is 0, which it will be at a particular point value, then the area under the curve has to be 0. So by definition, the probability of observing any element in the support of X is 0 in a continuous distribution. This is different from the discrete case. Okay, very important difference. So all we can do in a continuous distribution, what we are able to do, however, with a continuous distribution, is that we can always ask questions like, what's the probability of observing a value between these two quantiles, something between Q2 and Q1? What's the probability of observing that? And that probability, of course, is going to be the area under the curve. We can compute this area under the curve using one of the DPQR family of functions, as I will show you. Okay. So let's do this. How do we compute the probability of observing something between, two quantiles like x1 or x2? You can call the quantiles anything. You can call them q1, q2, x1, x2, whatever. So the kind of question I want to ask with a continuous random variable is, what uh, um, what is the probability of observing a value between x2 and x1? That's the kind of question. Graphically, it amounts to this thing. This is what I've shown here. Instead of Q1 and Q2, we could write X1 and X2, right? So what I'm trying to answer is the question, what's the probability in this random variable of observing a value between X1 and X2? That's the question, X1 and X2. So that's the kind of question that we will often be asking ourselves. It'll be a theoretically important question for us when we are doing science, okay, when we're doing experimental science. So that's why I'm teaching you how to do this. Now, given any probability density function, so let me come back here. So I just showed you one possible probability density function. So for the normal distribution, right? This is one probability density function, 1 over 2 pi sigma squared exponent minus half x minus mu over sigma squared, right? That's one probability density function, right? So this one, I can write this function in a simpler way just to make life easier for myself. Mu and sigma are understood, so I'll just write f of x now to represent this function. Now, as I said, this probability density function represents allows me to compute the probability of observing a value like x1 or something less than that. How would I do that? Compute the area under the curve, right? If I wanted to compute a probability like on the same function, if I wanted to compute something like the probability of observing x1 or something larger than that, what would be that probability? With the area under the curve here, right? That's the kind of cumulative probability that I would compute using the probability density function f of x, that same function. Okay. So how do I compute this area under the curve? Well, mathematically, the way we compute the area under the curve in a continuous distribution is by summing up the area under the curve, and that summation term is written like this. It's an integral, and so it's written like this: x1 to plus infinity, right, would be this mathematical statement here is calculating the area under the curve from x1 all the way up to plus infinity, right? All the way up to plus infinity here. Okay. So this sign here is called the integral. If you've never done integral calculus or differential calculus, this might be the first time for you. But this is a summation sign. This sign is just a way to write a summation, and it's saying that sum up the area under the curve to the right of x1 and tell me what that number is. That number is going to be a probability. That means the total area under the curve has to be 1, because that represents the probability of observing any of the possible elements in the support of x, right? So what I'm showing you here, this integral sign is telling you a way to describe the cumulative distribution function, because if I write If I have a question like this, what's the probability of observing a value like X or something less than that? Right? That is exactly the cumulative distribution function that we are asking about, right? That's how we would write that cumulative distribution function. And in the normal distribution, what that amounts to asking is, in a function like in normal distribution like this, what's the, so if I'm asking about f of x1, what's the probability of observing this number or something less than that? That's the area under the curve here. And this cumulative distribution function answers that question, right? So how do we do this? How do we do this calculation? Now, we don't need any calculus in this course. We are going to use a built-in R function for computing this probability. Okay. So what would that function be, right? You've already seen the DPQR family. You've already seen the DPQR family. So we are now talking about computing the cumulative distribution, cumulative probability of a particular quantile. Okay. And so obviously we are going to be using one of the DPQR family functions. Which one is that? Well, it's going to have to be the P family of functions, right? So in the case of the normal distribution, there's a built-in function called P norm that allows you to compute this cumulative probability of observing X or something less than that, right? So that's how this works. So that's where I'm going with this now, okay? So let's work through this, okay? So first of all, I just want to tell you some important properties of the normal distribution. And in particular, I want to talk about one special case of the normal distribution called the standard normal distribution. A standard normal distribution is just the normal distribution that I just defined, but with mu equal to 0 and standard deviation equal to 1. It's a special distribution that shows up over and over again in statistics. So it's important to, name it so that whenever I say the standard normal distribution, I'm talking about mu equal to 0 and standard deviation to 1 equal to 1 in the normal distribution. Now, in the standard normal distribution, one important property of it is that for x values ranging from -1 to +1, -1 to +1, the area under the curve will be 68%. The area under the curve for values ranging from -2 to +2. So technically, this is not correct what I'm saying. It's technically -1.96 and +1.96, but I'm lazy, I don't like to write decimal points. So let's say -2 to +2, right? So the area under the curve between -2 and +2 is going to be about 95% in the standard normal. Yeah. And similarly, between -3 and +3, the area covered under the curve will be 99.7%. These are invariant properties of the standard normal distribution. Okay? So please remember this always, that if we go +2, -2 around the mean, we cover 95% of the area under the curve, right? So the probability of observing a value between +2 and -2 in the standard normal is going to be about 95%. Very important property. Yeah. Now, more generally, right? So right now I was talking about the standard normal distribution, right? But this generalizes to every normal distribution that we can imagine. So for any possible value of mu and sigma, what will be true is that the probability of observing a value plus one times or plus minus times the standard deviation will be 68%. 68%, right? So here standard deviation is 1. Therefore, I'm talking about +1 -1. But if standard deviation was 2, then this range that covers 68% of the area under the curve would be +2 and -2, right? So it depends on the standard deviation, because remember, the standard deviation controls the spread of the distribution. So minus and plus 2 times the standard deviation to the left and right of the mean will cover 95% of the area under the curve, and minus and plus 3 times the standard deviation to the left and right of the mean will cover 99.7% of the area under the curve, right? So these values, these -1, +1, -2, +2, -3, +3, these will be called quantiles. And uh, well, actually, what I wanted to say is that the um, depending on the in the standard, sorry, let me correct myself here. Okay, so in the standard normal distribution, these -1 plus -1 +1 -2 +2 -3 +3, these will be called quantiles. For any other normal distribution with a different standard deviation, the quantiles will be with reference to the standard deviation. So this will be a quantile, this will be a quantile, -2 times sigma, -3 times sigma is a quantile, +1 times sigma is a quantile. So when I refer to a quantile, I'm talking about this quantity here, right? These points in the normal distribution that cover certain areas under the curve times the standard deviation will give us the quantiles. Okay, so this is also something I should have written more precisely here, right? Okay, so let's look at some of the key functionality, of the DPQR family of functions in the normal distribution, right? So just like in the binomial, this is now more of the same, except we are in continuous space now. Okay? So as I said, we can compute the area under the curve between any quantiles, right? X2 is larger than X1, so I'm going to compute the area under the curve like this, right? Here's my distribution. Here's the x-axis, right? I'm going to compute the area under the curve between x2 and x1 using the p norm function. So let me do that. Okay? So let's say we are talking about a normal distribution. Let's say we are taking a normal distribution like um, um, standard normal, okay? Mean 0, standard deviation 1. So the probability of observing 2 or something less than that will be 97.7%. So what I'm computing here in the standard normal is the probability of observing 2 or something less than that. That means this area under the curve all the way to minus infinity, right? All the way to minus infinity, right? So that's 90, what was it? That was 97.7%. 97.7%, right? Now, if I want to know what the area under the curve is between -2 and +2, what I'm going to do is I'm going to subtract this cumulative, this probability to the left of that. And that will leave me with, this probability, right? This is what I want. So what I'm going to do is I'm going to compute the area to the left of 2 and subtract from it the area to the left of -2. And that is 95%. Like I said, right? That's exactly what I said earlier. That's just a fact about the normal distribution, that the area between -2 and +2, or technically -1.96 and +1.96, is about 95%. Okay? So, so what that means is that the area in the tails here is going to be 2.5% each, right? Because 95%, if the center mass is 95%, the tails, which are in a symmetrical distribution like this, will have to have equal probability, and the total probability under the curve has to be 100%, right? Or 1. Therefore, the tails will have 2.5% probability, right? So what that means is that the probability of observing -2 or something less than that is 2.5%, and the probability of observing +2 or something more than that is 2.5%. Okay. So that's the usage of the p norm function. The p norm function allows you to compute these probabilities. P for probability, right? Okay. So so here are some examples of how to use this. Okay, so in the Bernoulli and the binomial, we had used the DPQR family, and so here's the binomial case. We had used the DPQR family. We're going to do the same thing now with the with the DPQR family in the normal distribution. Okay. So how does this work? So let's take the standard normal again, right? If I want to compute if I want to generate 5 random data points from the standard normal distribution, I'm doing that here. You see that with the the R norm function, right? Now, remember that, in all these R functions, there are some default values that are set in the function itself. So in the R DPQR family of functions for the normal distribution, the mean and standard deviation is by default set to the standard normal because it's used so frequently. So that's why I could just write R norm 5 to generate 5 random data points from the standard normal distribution. If I wanted to generate data from a different normal distribution with a different mean and standard deviation, right? I want to generate 5 data points from a standard distribution with mean 500 and standard deviation 100. I could do that, right, by defining the mean and standard deviation. But if I don't define anything here for the mean and standard deviation, I'm sampling from the standard normal distribution. Okay, that's what's going on here. Now, I can compute these probabilities. I just showed you how to do that. If I write pnorm2 is computing for the standard normal distribution, it's telling me the probability of observing 2 or something less than that in the standard normal. But I could ask a question like this for a different distribution, for a distribution with mean 500, standard deviation 100. What's the probability of observing a value like 200 or something less than that? That's 0.001. Okay. I could even ask a question like, what's the probability of observing a value like 200 or something larger than that? How would I do that? I would just do 1 minus this because now I'm looking at the area to the right of 200. And I know that the total area under the curve has to sum to 1. Therefore, I just subtract from 1 and I get the area to the right of 200, and that's 99.8%. Okay. So that's how you could do this calculation. If I wanted to know, for example, what's the probability of observing a value between 200 and 100, how would I do that for this distribution, right? So for this particular distribution, I would write the probability of observing a value between 200 and 100, it would be 0.0013, right? So I could ask another range. Let's say, what's the probability of observing a value between 800 and 100? That's 99.8%, right? So these are all questions you can now answer for any arbitrary normal distribution, right? Another way to ask a question like, what's the probability of observing a number like 2 or something larger than that in, for example, a standard normal distribution, you could set lower dot tail equal to false. That will compute the area to the right of the curve. So graphically, what that amounts to is something like this. So if I have a distribution like this, right? Standard normal, this is the standard normal distribution, often written N01, right? If I want to know what's the probability of observing 2 or something to the right of it, I set lower dot tail to false, lower dot tail to false. That gives me the area to the right of it, of that number, right? 2 lower tail equal to false, right? That gives me the area to the right. I could have done this in a different way. I could have computed the area to the left of 2 and subtracted that from 1. I get the same number, of course, right? There are 2 ways to do this. All right. So that's that. And just like the Q binomial function, we have the inverse of the CDF, which allows us to find out the quantiles such that the area to the left of it is some particular probability, right? So here, what I'm doing is I'm asking the question with the Q norm function, what is the quantile such that the area to the left of it is 0.977, right? That's what this question is answering. And notice that the denorm function, which I already showed you the usage of, is actually telling me the, for any x value, it's telling me the, um, the value on the y-axis that constitutes the curve that we actually drew, that bell curve that we drew. So this number is not a probability, it's a density. And that's what this letter D stands for, right? So In R, they use in the DPQR family, they use the letter D in the D norm and the D binom and the D burn function to stand for density, right? Even though in the discrete random variable, what we're computing is not a density, but a probability, right? They still call it a density, but that's just in order to be consistent, right? They just want to be consistent in the creation of the DPQR family. So, you could imagine that um, in the discrete case, they have, for example, the D binom function in the continuous case. In the normal distribution, for example, we have the D norm function, right? Now, these two functions are computing two different things, right? In the D binom function, we are computing the probability of every discrete event that can happen. In the D norm function, we are computing the density, right? This is a crucial difference between these two, but both are called D. Both functions start with D, right? So you just have to remember that the meaning of the D binom and the D norm function is quite different here, okay? The R developers did this just for convenience because they wanted to have similar names for the function that actually describes the shape of the distribution. That's why they called it D binom, right? They would have had to use some other letter here, and that would have just caused confusion, right? So that's why they did that. So that's why we have the D binom function, even though it computes the probability in the D norm in the continuous random variables, and there are many other random variables that are part of the continuous random variable family. The D family of functions is not computing a probability; it's computing a density. Okay, just remember that. And the meaning of the density really is what you can try to understand the meaning of density here in the continuous random variable as the following. So whenever you have a distribution like this is a high density value, this is a low density value, right? So this value is a high density value here. This is a low density value. What the meaning of these is that if a particular numerical value on the x-axis has a high density value, there's the high density value. What that means is that you often have um, you have I'm sorry, I've got a visitor on my Zoom, so I'm trying to end my lecture now. So you're going to have um, uh, high probability of observing a value near x1. That's what the high density means. Okay. All right. So I'm going to stop my lecture now because I have another meeting. But this is the basic introduction to the discrete and continuous random variables. Right. So I will continue this lecture in a second part. I'll upload that lecture later on.